it amuses me to do this like this. If we put the two of them together, then we might get some kind of intramolecular Williamson ether synthesis. In this case, we would form that beautiful heart-shaped ether for Valentine's Day. So this actually becomes a way of constructing cyclic ether systems, right? And of course, if we now kind of tailor it to be something more realistic, 1, 2, then if we treat that compound that has an OH and a Br on the same thing with sodium hydride, then chances are we're going to get deprotonation of this intramolecular attack, and in this case we would make an ether that's a 6-membered ring. That could be a way to make tetrahydrofuran. That could make a 4-membered cyclic ether. And if we envision what's going on here, you know, deprotonation would occur first, and then, you know, this end of the molecule has to kind of swing back around and hit the right spot for that to fall off, right, to get the intramolecular attack. Okay. Now, an interesting thing happens when we get to that point. Because now, if we consider the electronics of this system, this carbon here, because it's next to this bromine, is already partially positive. So there's already some kind of attraction for the lone pairs of electrons here on the oxygen to that partially positive carbon. Okay. So there's a tendency for this to be wanting to happen already. I'm not saying that it would just happen on its own, but it kind of wants to be happening because of the proximity of those lone pairs with that partially positive carbon. So what you find in a situation like this is that where we had to use that really, really strong base sodium hydride for everything else, you actually don't need such a strong base to get this to happen. So therefore, we could get this reaction to occur with just our regular old sodium hydroxide, because the hydroxide anion, because of the tendency for that wanting to want to happen, although you don't think of a hydroxide as a strong enough base typically to deprotonate an alcohol irreversibly. The driving force for this to want to react here and kick that out makes it easier for that deprotonation to occur. Yes, Alex?
What prevents, because like if we're doing a reaction like this, what prevents one molecule doing S2 on the other molecule? instead of just cyclonizing.
Okay, I'm going to let you demonstrate for me.
Sweet.
Okay, hold up your hand. All right. Now just slap your own face for me. Okay. See, usually I do it to myself, but since you're asking, I can let you do it. Okay, see how easy that was? Because it was just one part of you combining with the other. Okay? Now try to reach over and slap deep in the face.
Don't let him do it.
Okay, so what you try to do now depends on two particles colliding, right? Now, if Deep is a smart guy, he's not going to just sit there and let you slap him in the face, right? He's probably going to run from you. So that reaction depends on you being able to collide with him with the right orientation and energy for the reaction to occur. So whenever there is a choice to do something intramolecularly versus intermolecularly, the intramolecular process is always faster, right? This is exactly the same reason why we're saying like a hydride transfer, if you can get a carbocation rearrangement, that can happen faster than something else attacking, you know, an existing cation. So similarly here, you know, when you make the alkoxide, yeah, the alkoxide could go and attack a different molecule, but statistically, it's much more likely to happen to attack intramolecularly than intermolecularly. Good question. All right. So the idea is, if we kind of neaten up our arrows a little bit, I could do a little single arrow thing there. The idea is that with an intramolecular Williamson ether synthesis, where you only have a two carbon length between the OH and the Br, right? That can occur readily in the presence of sodium hydroxide. You don't need a stronger base for that. Okay? And what is it that we're making here? An epoxide. So epoxides can be synthesized by this kind of intramolecular Williamson ether synthesis. What do we call this kind of molecule? We've seen it before. Where have you seen a halohydrin before? What was that, Henry?
We can make them from alkenes.
Right! So if we took an alkene, then we could convert it into a halohydrin. And what would be the reagent system? So here you have a two-step method for synthesizing an epoxide from an alkene. But you also know a one-step method for doing that? One famous example, MCPBA, some kind of